Okay, without further ado, let's actually do something. So, today we'll talk about analysis of variance. This is the crux of the rest of the course. Okay, so it's important that you, if you don't understand something, you ask, okay? It's really important. So, let us talk then of analysis of variance. So we've talked about t-tests and z-tests for differences between groups. And they're fine, they work, they do the thing. They're good for two groups, they're good for single groups. But what if we have more than two groups? And of course, as you probably know, in almost every single experiment you have ever read or ever seen, there are more than two groups. It's not usually just one experimental group, one control group. It's usually a variation on that, right? So we need something then that's going to do more than one group, more than two groups. So okay, here's a situation, and the numbers don't matter, so don't feel like you should worry about the numbers right now. I don't even know what this is. So, but we have a thing called A. This might look familiar. You have an assignment coming up that has 4 levels of A. This one has 3. So we have 3 groups, and A is just a variable, an independent variable. It has 3 levels: A1, A2, A3. And we have 4 means, and we're trying to see if these 3 groups differ somehow. Now, from our lecture on power, you should know that obviously that's going to be very difficult here with 3 subjects per group, but it's conceivable, who knows? Anyway, the important point here is that we have more than 2 groups. So, here's the question I want to ask you. Why do the scores vary? Okay, so why are any of the scores different from each other? In other words, what are the sources of variation? Okay, so where does variation come from? Where does variance come from? Well, individual differences, obviously. So if I have a group of, let's put U3 here, and then we have a group of 3 back here, that's good. And we have a group of, there's group 3 here. So there's U3 here. And if I give you any kind of test, the next quiz, which is on Thursday, your scores will differ, yes? And one of the reasons they'll differ is you're different people. Okay? They're gonna differ because you're different. You're all very special snowflakes. So when I make these sarcastic remarks, I'm always concerned that you can think I'm serious because you can't see the smile on my face. And there's going to be group differences. I don't know. We have a group here, and a group back here, and a group here, and maybe when you're sitting here, it's more ideal to see things and hear my, frankly, booming, very masculine voice. Again, some of these are jokes. Thank you for courtesy. So that's potentially a reason. Or I could have treated you all differently. I mean, I haven't. So maybe I gave you guys a placebo, you guys got 2 shots of vodka, and you guys had 4. So you guys probably didn't do the best. I was doing the best. So group differences would be the other reason. So any score then equals some combination of just an overall base level of being a human that everybody gets, plus the group differences. So we got no vodka, 2 shots, 4 shots. By the way, that's totally doable. Not from me to you. But I'm saying those experiments actually are done, and the way it's done is everybody gets 4 shots, but when they all taste so heavily of peppermint, you can't taste the alcohol. And believe me, I've been in one of these experiments, you can't taste the alcohol. And people who get the placebo actually act drunk. It's amazing. And then you have them blow, because you can't let people leave the lab to blow into the legal limit, right? So my old colleague, my Penny, she used to, I was a grad on this postdoc, and she used to do these experiments, and the control group could leave right away, but the other groups had to stay, and what they would do is she'd say you could leave when you blow below 0.05, and she'd take their car keys when they came in, and she just had movies set up and popcorn, and people just hung out, and every half hour they moved the club. But it's funny because you'd sometimes see people walking around the site department. It's 2 o'clock in the afternoon because they had 4 shots of vodka at 10 o'clock in the morning. So you can do that experiment. So sort of a base level, and then plus the group differences plus individual differences. That makes sense, right? Oh, let's turn it into math. So x equals mu, that's the grand mean, plus tau, a treatment effect, plus epsilon, and that's error. And that's what we call individual differences error. We do that a lot in statistics, things that we can't put our finger on, things that are left over. In fact, sometimes we call them residual. But error is fine, epsilon for error, okay? X equals mu plus tau plus epsilon. Say it to yourself 5 times every night before you go to bed. Okay, good so far? Questions? So that's called the structural model of analysis of variance. X equals mu plus tau plus epsilon. Any score equals the grand mean plus the treatment effect plus error. And again, error is just individual differences. That's all error is in this case. Okay? All right. I've made it bigger. Okay. Let's make more than one assumption. Let's start with this one. We're going to assume the null hypothesis is true. We always start that way, don't we? You always start with the null being true. We're trying to prove that's not true. We start saying it. So if the null is true, then mu1 equals mu2 equals mu3 equals ... equals mu k. Mu sub k, there are k groups. In our case, there are 3. K could be 60. In this case, though, it's 3. So if they all come from the same distribution, they're all the same. They also would all have the same variance, wouldn't they? So sigma squared sub 1 equals sigma squared sub 2 equals sigma squared sub 3 equals ... sigma squared sub k. So that's just H always true. All inferential statistics start this way. Right? Okay. Good so far. This is good. It's just the null hypothesis. Just the null hypothesis, that's all this is. Let's keep assuming things. Scores are randomly and normally distributed about the grand mean. Yeah, okay. So if we drew a distribution of all 9 of your scores, we would get something that looks roughly like the grand, like the normal. And that's not a ridiculous assumption. You can also violate the crap out of it. Turns out, but it's a reasonable enough assumption. Especially considering it comes from samples and the central limit theorem and all that good stuff. The observations are independent. This one we cannot violate. We can violate the normality thing. We violate it like crazy. We can't violate independence. So if I know your score, I don't know your score. Okay? There can't be any effect of one person's score on another person's score. Well, the model says x equals mu plus tau plus epsilon. It doesn't say also if you're sitting beside that other guy. It doesn't say that, right? All this flows out of the model. X equals mu plus tau plus epsilon. There's no except on Thursdays. There's no, and if you're sitting beside this guy. There's no, and if you're in this seat. Okay? So I'm assuming all of the sources of variation are actually in the model. Which also, again, makes sense, I think. Okay? All right. So all the sources of variation are in the model. Independent observation. Scores are randomly and normally distributed about the grand mean. Okay, now it's going to get, whoops, let's go back. It's going to get a little mathy here. Here we go. As I said, I never said there'd be no math. Okay. Let's just look at variances. So, you know that sigma squared sub 1 roughly equals s squared sub 1. So In other words, the statistic is an unbiased estimator of the parameter. The wiggly equals here mean approximately, pretty much. Sigma squared sub 2 equals s squared sub 2, etc. Sigma squared sub epsilon, that's the variance of individual differences. The variance is due to individual differences. Should equal just the overall variance. Because remember, we're assuming there's no difference between groups. We made that assumption. So that means all, write this up on the, start writing this up here. So just x equals mu plus tau plus epsilon. By the way, writing that on a blackboard is very comforting for me. I haven't done that in a long time, and it's extremely comforting. It makes me feel very good. But we said there's no differences. We made that assumption, so that's nothing. This doesn't change. Mu doesn't change. So in other words, there's only one source of variation if there's no difference between groups. And that's this, epsilon. So if we were to take the variance, calculate it, s squared, it should equal sigma squared sub epsilon. Okay? That's fine. This is where it gets a little weird. If I took the variance of the three groups, so we got, let's see, you three are a group, right? Yeah. So I took your variance, and then I took your variance back here. It's actually an AV connector, which used to be, it's also, anyway. You think it was hard last week, we hooking things up, you should see what it used to be like. We could pull things up from the floor, and I'm not kidding. Now you guys have a variance. So one variance here, one variance here, one variance here. If I took the average of those three variances, the mean, and let's call that S bar squared. Okay. And the J just means the J stands for groups. J is 1, J is 2, J is 2, group 1, group 2. So if I took the average of all your variances, that should equal the variance. Because there's only one place variance can come from. Because the null hypothesis is true. And you're saying, Dave, you can take a mean of variances? The numbers don't know where they come from. This just equals each variance, group 1, group 2, group 3, divided by the number of groups. Questions? This is the first, perhaps, potential stumbling block. Okay, this is good. Either I'm explaining this very well or horribly. Or you're very smart. Let's say I'm explaining it very well, you're all very smart. Now from the central limit theorem, we know that the variance of x bar is sigma squared over n. That's just a thing. So the variance of the sampling distribution of the mean is sigma squared over n. That's just true. Okay, that's from the theorem, not my theorem. So it's kind of the same. S squared sub x bar, it's basically, except that we're using it as using a statistic, equals sigma squared sub epsilon over n. But let's do like we did with the other one, and then let's isolate sigma squared sub epsilon. All I'm doing is cross multiplying. S squared sub x bar times n. So that should also equal sigma squared sub epsilon. So right now what we have is, so right now what we have is this, and I gotta remember, screw this up, S squared. These three things, these two things, both equal this. So S squared over K is the average sample variance divided by the number of groups. Should equal the average sample variance times the number of observations. should equal this. They all should equal the same thing. Okay. By the way, I would never test you on this. I'm trying to show you the background, show you how it works. The point of this course, it's a couple of them, but one of them is to show you why things work and how they work, so when you read a paper, you can go, oh, sure, that. Though I think knowing this is certainly valuable. Knowing that, but I'm not going to test you directly on this. But if I told you that the variance of all the scores was, let's go crazy. That variance of all the scores was 25, you should know that that's an estimate of something. And the estimate it's an estimate of is sigma squared sub epsilon. Okay. We actually now have two estimates, right here, sigma squared sub epsilon. That's kind of cool. Two separate estimates. We got this one and this one. Oh, look, it's exactly what I wrote here, except it's nicer. It's nicer font, because it's not my horrible handwriting. We have two separate estimates of sigma squared sub epsilon. That's called mean square treatment on the left. That's called mean squared error in the middle. So if you remember last year in 2126, how many did I teach 2126 on 1 and 2 last year? The rest of you had Dwayne? Is that what happened? We're bastards? You guys know like we're all friends, eh? And doing that is fun. I only make fun of people. With Paul, I get sometimes a little out of hand. Sometimes when we're not in a global pandemic, he would walk by classrooms every day and stick his head in and say, I wouldn't believe anything he could see. Sometimes I'll look at his classroom and just make jokes about how much he weighs. Well, very well. Anyway, if you remember in that class, you talk about mean squared treatment, mean squared error, and mostly what we do in intro stats is we just say, yeah, don't worry about what they are. Well, here, this is what they are. Okay? So if HO is true, the expected value of mean squared error is sigma squared sub epsilon. The expected value of mean squared treatment is sigma squared sub epsilon. They should be, they're both measuring the same thing if HO is true, because the only place variance can come from, as you can see over here on the blackboard, is individual differences. This is where it gets, to me, interesting. And I mean, I know none of you probably find this interesting in the least, but this is where it gets interesting to me, because if HO is not true, the expected value of mean squared error is sigma squared sub epsilon, but the expected value of mean squared treatment is sigma squared sub epsilon plus the number of observations per group times the variance due to treatments. Okay? So if HO is not true, mean squared error still equals just an estimate of sigma squared sub epsilon. But if there is an effect, if the groups actually are different, we have some other value here. N, that's the number of subjects per group. In our case, it's 3. Times sigma squared sub tau. Okay. Okay. So that means then the expected value of mean squared error is less than the expected value of mean squared treatment. Could it ever be the case that the expected value of mean squared treatment is less than the expected value of mean squared error? Is that possible? Just look at the things there. Don't worry about it. Just look at it. Tell me. What do you think? Is it possible for mean squared treatment ever to be less than mean squared error? Shouldn't be. But did you want to say something?
I was just going to say no.
Yeah. Why not?
It doesn't make sense for, I mean, I missed a little bit of the
No, you're
beginning,
fine, you're fine.
But if I'm taking any statistic from the same place, there's no reason that the error should ever be less than the...
Also, look, this is a squared quantity. This can't be less than 0. So this always is positive or 0. This can't be a negative number. Right? Because you can't have a negative number of subjects per group. And you can't, this is squared. It's sigma squared sub tau. It's got squared in the freaking word. It can't be negative. It must be positive. I'm going to tell you something else. Sometimes it comes up and you get an F. That way you do the whole thing. And it turns out that it actually is less. That tells you that's the violation of an assumption. That's what that says. Okay. So now I think we're getting to a point where you can start to see like, oh, okay. So that's where this comes from. That's where the idea of the test to see if the groups are different is going to come out of this. Okay? So if we were to divide mean squared treatment by mean squared error, so mean squared treatment divided by mean squared error, we'll have some estimate of how much extra variance or variation mean squared treatment is actually measuring. And this again is where we're getting to the point of something useful and cool. Is that one of the Apple pencils?
Yeah.
Is it good?
Yeah.
I've got a knockoff one. It's fine.
It's probably about it.
That's the reviews that said it's a pen is good. Yeah, but I still think it's good. Mine doesn't charge just by sitting at the corner of my iPad. So in other words, tau. Let's just call it tau, sigma squared sub tau, tau, whatever. This is precisely what analysis of variance does. It checks to see if there's extra variance being measured by mean squared treatment. So that's why it's called analysis of variance. We are analyzing variance to find out if there's difference between means, which is kind of, I know when I first heard about it, I thought, this is really weird. Like when I was a second year stats, the course from last year, when I took second year stats, which is 1985, right? Oh, by the way, in second year stats, I was this guy. Yeah, I don't understand. Yeah, but why? It's like I was a toddler. And eventually I was told, there's a course next year you'll have to take if you want to do the honors program instead of this course, where we answer all those questions. Okay. So what we do is we divide mean squared treatment by mean squared error. That's what we're going to end up doing. It's called an F ratio named after Fisher, R.A. Fisher, who also, as an aside, was a flaming racist. But that doesn't mean his math was bad, it just means he was a racist. Racists can do math too. And it, in the 1920s, it wasn't like that sort of everybody was racist then. It's like, you know, it's not like, oh, that's grandpa, he's a bit weird about stuff like that. It's like, no, he was, yeah, just saying. So it's F after Fisher. He didn't name it after himself, by the way. Someone else said it's called the F ratio. So what's the expected value of F if HO is true? So what's F? F, again, is mean squared treatment divided by mean squared error. What is the expected value of F if the null hypothesis is true? Please.
Sigma squared F long.
Give me a number. Give me a number. No, that's fine. Don't be sorry for saying something. That hurt. I'm getting old, and I can't be, but I can't not be all active and stuff in class. But one day I'm gonna hurt myself, like badly.
Did you break your leg a couple years ago?
I broke my, yeah, no, listen, I wasn't preaching. Yeah, but in fact, it hurts literally right now, one of the places where they broke it. Here, here, and here. Yeah, it was fun. Give me a number. What's the expected value? It's not even just, yeah, it is sigma squared sub epsilon, blah, 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 blah.
Oh,
But turn that into a number.
crazy.
Well, these things should be equal, so what is it?
1.
1, yeah. Something divided by itself is 1. Because, let's break this up here. And instead of using sigma squareds and all that, I'm just going to use taus and epsilons. So, that's mean squared error, whoops. Tau plus epsilon. And sort of mean squared treatment, and mean squared error is just epsilon. But remember, if null hypothesis is true, tau equals 0. Epsilon divided by itself is 1. Okay? So it should be 1 if there's no effect. What if there is an effect? In other words, what if tau is greater than 1? Or greater than 0, sorry. If tau is greater than 0, oh, it's going to be greater than 1. I can't put a number on it, but it's going to be bigger than 1. These are all squared quantities. This thing should never be less than 1, this whole quantity. It really shouldn't ever be. If it is, you've violated some assumption. Because all the math behind this is based on a series of assumptions. If you remember doing, geez, I don't know. If you remember doing proving identities and stuff like that in math or Euclidean geometry, and you would say assume the following, and then you could do the balance equations and stuff. Do they not teach math in school anymore?
Nope.
Mostly Googling.
That's like discrete math here.
Yeah, yes, it is discrete math. It's actually literally exactly. I guess I had grade 13 when I was in school. Dr. Hotshot here took all 3 just math courses in grade 13. Calculus, algebra, and functions. Failed a bunch of tests in algebra, which were about probability and statistics. I'm sure now you have a great deal of confidence. By the time I got to stats in university, I was fine. I was scared shitless though. It's like, oh my god, it's this stuff. I failed this part. But then it's like, oh, I guess it's stuck, because now I know it. So this now should be greater than 1 if HA is true, or HO is not true. You can say either. So if HO is true, mean squared treatment by mean squared error will be distributed as F, and it's got 2 sets of degrees of freedom. We are estimating 2 variances, so there's going to be a variance, or degrees of freedom for the numerator, and degrees of freedom for the denominator. It's going to be both. Okay. If not, it'll be distributed some other way. So what we end up doing is we end up looking up in a table to see if the groups are different. To see if we get a critical value, well, also the groups are different potentially. We get a critical value with a certain set of degrees of freedom, and then we go look it up and see if we've exceeded that value. Okay. Questions? We're half an hour in, and you haven't asked one. Make sense so far? If so, that's wonderful. Okay. So if it's unlikely to be distributed that way, in other words, if we exceed a critical value, if it's so unlikely that there's less than a 5% chance, it's what we usually go with, because for some reason, a lot of people still worship the 0.05 level of significance. It's distributed some other way. We say the groups must not be the same, they must be different somehow. Because if there's only one thing left, if the null is all the groups are the same, the alternative hypothesis is at least 2 are different. It doesn't say which 2, by the way. It just says at least of our 3 groups here, at least 2 of them differ. Could be all 3 different. Could be just 2 different. the calculation doesn't figure that out. It just finds out if 2 of the groups are different. And that's true if you have 3 groups or 27 groups, doesn't matter. It just tells you at least 2 differ. Okay. So what we do, again, this gets a little more mathy. I literally don't mind wearing a mask, doesn't bother me at all. The only time it bothers me is like when my nose gets itchy, and it's like, what do you do? Do I run away and go to the roof? I'm not going to do that. That would be weird. So we have sums of squares. Sums of squares, think about it, when it's a sum of squares, I mean, it's in the name. It's a sum of squared values. But let's just go to a very simple, the simplest possible thing we can think of, which would be just sample variance. So it's x minus x bar squared over n minus 1. Sorry, x minus x bar squared over n minus 1. Right? And you sum them. You sum the squares. It's called sums of squares because you are summing squares. It's a very good descriptive name. So a lot about statistics, one of the things I can say is that the names are sensible. There is a total amount of sums of squares of square deviations from a mean in any batch of numbers. So if we had, U3, 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 we had the 3 sets of scores. We could figure out a grand mean for all of you. Sure, why not? Could. I'm not going to. Could, because I've given you scores, so I'm not going to go through that right now. But we could calculate that, and we get the square deviations from the mean. We can partition this into the sum of squares for treatment and the sum of squares for error. They should add together to form the sum of squares for total. The sum of squares for treatment is going to be your mean, so your group's mean, minus the grand mean, plus your group's mean minus the grand mean, plus your group's mean minus the grand mean with a square over this. So your group's mean minus the grand mean squared, your group's mean minus the grand mean squared, your group's mean minus the grand mean squared. Okay? Sum of squares error is going to be your group mean, so your individual scores minus your group mean squared. We'll do that for all of you. Then for all of you, we're going to take each of your scores minus your group mean squared. Sum of them. We're going to negatives. Put those two things together, you get sum of squares total. The degrees of freedom we have, any design has a finite number of degrees of freedom. If we have our design here, when we have 3 and 3 and 3, we have a total number of degrees of freedom of 8. Right? We have 8 degrees of freedom. Because we have 9 minus 1. Degrees of freedom for treatments should be the number of groups. We have 1, 2, or 3 groups minus 1. So k minus 1 we'll call it, or in our case, 3 minus 1. And then for error, our degrees of freedom for error, well, they're basically just, again, it's always the bottom part of a variance equation. So it's little n minus 1, so that's 2, plus little n minus 1, so that's 2 more, and little n minus 1 is 2 more, so in our case it's going to be 6. Oh, 6 and 2 is 8. I said it was 8 total degrees of freedom. I'm not lying. So getting more precise, and again, this is something I wouldn't be asking you. Computers do this for you. The math, there was a time when people did these things by hand. I would never, ever, even in the second year stats, require people to calculate these things. You all have, avail yourselves of free copies of SPSS. They work until the end of August. And if you can't get it to install on your computer, maybe you've got a Chromebook or something. If you have a Chromebook, though, I think you can use something called JASP. But if you don't have a copy of SPSS, we have them in the computer labs. So for doing your next assignment, it's probably easier to use SPSS. You can do it this way. Well, I don't care. So that has n-1 degrees of freedom, so that's total. There's mean squared treatment. The G is grand mean. The J is group mean. So each group mean minus the grand mean squared. There's two summation signs? Yeah, well, within each group we do it. So we add up all the scores minus the grand mean squared. And then we get a number. Then we add that again to this, do the same thing again, add it again, do the same thing again. That's why you get two summation signs there. And it turns out that's big N minus K. Big N is the total number of observations, which in our case is 9, minus K, which is 3, which is 6. But big N minus K big N minus K actually just equals K times little n minus 1. K is the number of groups, little n is the number of observations per group. So if it's K times n minus K, I'm just expanding it. What's K times n? Number of groups times the number of people per group. That's big N. So it's just big N. Okay. So that's not some magic thing, big N minus K. It's just, oh, please, yes.
I think I missed it. Why did you say there's two summation signs?
Oh, yeah, because so for doing this, we're going to take each group score within a group, individual score. We're going to subtract the group mean, right? We're going to square it. We're going to do that for this group, and then we're going to do that for this group, and then we're going to do that for this group, and then we're going to add them all together. That's a good question. We're eventually going to see designs. Eventually, I stop showing you this part because it gets crazy. More complicated designs. But you're going to see ones with 3 and 4 summation signs. That's just because you've done it again and again. You're taking this group and this group and this group, and you sum all those together. And then you do it again, and all this other groups, you do it again. Right? It is so liberating not sitting in a chair. Well, okay. So what we end up getting is something called an analysis of variance summary table. And if you use SPSS, which again I encourage you to try, I have posted a video on my YouTube channel at daveBroadbeck.com about how to basically do assignment 2. And it shows you how to do an analysis of variance with SPSS. So take a look at that step by step, and you'll see that you end up getting something called an analysis of variance summary table. So we have between group variance and within group. Sometimes this is called, it might be called A, because we had to call our variable A that time, and error. It could be called treatment and error. It could be called treatment and residual. They all mean the same thing. So we get this, and when we get it spit out in SPSS, it actually gives us the numbers for these things. So we get these. There's between groups, within groups, and then the F value is done taking mean squared between divided by mean squared within. Okay. which is mean squared between divided by mean squared within. Questions so far? Barely. Great. You seem to be getting it, which makes me happy. So the mean squares is the sum of squares divided by the requisite degrees of freedom. And then the F value is just this quantity divided by this quantity. All right. So it's actually a very simple technique, but it's extremely powerful because now it's going to tell us if two groups differ and we have more than two groups. Like this went really fast. This is rough. This is really pretty easy to do. It really is. It simply involves, conceptually I think it's pretty simple. I hope it's straightforward, the idea of what's going on here conceptually. It's easy to do mathematically, arithmetically, obviously, because it's just a whole bunch of sums of squares and dividing. The problem is if you do it by hand, there's a lot of places to make stupid mechanical errors. It's very easy to make errors. When you do it with a computer, you're not going to make any mistakes. As long as you put the numbers in SPSS properly. And you can actually do it also in Excel, Google Sheets, numbers, the math program. That's all in there. But I would, if I were you, I would learn how to use SPSS if possible. This only tells you that two means are different, but not which two or three or whatever. It tells you that two means differ from each other. And it's about the overall pattern. So some people will say that, well, I want to know what two means exactly different. And that's a different question. There are further analyses you can do with, there are further analyses you can do that allow you to determine which two means or which more than two means differ. But a lot of times what you're interested in, why did my voice go up so high there? A lot of times what you're interested in is an overall pattern. So if we had our mythical experiment here where you're getting no vodka, and you're getting 2 shots, and you're getting 4 shots, we expect a pattern. And that pattern is different from, we would expect something like, if this was, let's make a number of words recalled on a list. We would expect the group that's had no alcohol to be best, and the group that's had 2 shots to be less, and the group that's had 4 shots to be less. We expect a pattern like that. We simply don't expect them to be the same. You might be interested to know if these two here are different from each other. And there's a way to do that, which is Thursday's class. But it's also possible, it's also the case very often, that let's say you had like a whole bunch of control groups. So let's say you had one control group that we had you did the thing with, everybody got 4 shots, but it's so laced in peppermint oil that you can't tell. This is why there's alcohol. But then let's add another group here, you're not going to get anything to drink at all. You would expect those 2 groups to be the same. So very often what you get is if you have like control groups, and you see like, if you see something like this, 3 the same and 1 like that, I don't think there's any need to say which 2 differ. I have eyes. Even my eyes can tell you which 2 groups, that group differs from the others. I don't need anything further. But if you're very interested, you can expand on this technique to find out if this one differs from this one, this one differs from this one, and this one from this one. There are ways to do it. So, seriously, I'm kind of shocked, in a good way, that you don't have a lot of questions. Do you have any questions? Because I'm happy to answer.
I guess the question I have is like you said, we can just kind of look at it, see for ourselves pretty much all the time. So where would you want to put this in a paper? Like,
This goes in the results section.
it just goes in there just to show you did it.
Yeah, and usually your design is going to be a little more complicated in 3 groups, but sometimes they're straightforward. And I know when I've had honors thesis students that have one independent variable and they're doing, and they want to go further, I always ask them, so why? What was your hypothesis to begin with? Did you think only 2 groups would differ? Did you think what kind of pattern in your data were you interested in? And that's what this is getting at. And it's saying there's a pattern that isn't all equal. You can go further. You can do finer grained stuff. Like I said, we'll talk about that on Thursday. And there are techniques. And they're really pretty simple techniques. They're basically all riffs on a t-test. But just with these groups, but piggybacking on analysis of variance. But yeah, that goes in the results. When you read a paper, the intro tells you, when you get to the end of an introduction, if it's a well-written introduction, you as the reader should be almost yelling at the paper, why hasn't someone done this experiment? Because a decent academic writer, scientific writer, leads you along a little path, and then this was done, and this was done, but that wasn't done, and this was done. Reader, that also wasn't done, but then these other guys did it, and you know what, they didn't do it either. And you want to see you should do it. And if your thing is that one group should be crazy and the other group should be down here, I don't know why you want to go any further. I love statistics. I find it truly fascinating. And I know that's very odd, but that's fine. But it doesn't mean that I think you should just be doing them for just because you want to crank up more stats. And I'm very often one of the reviewers when I review articles for journals who says, why did you do this much analysis? It wasn't really necessary. So yeah, I mean, one of the downsides of the fact that it's all doable by computer and very complicated analyses, not things like this, really deep stuff is can be done by computer. It used to be that you had to book time with some computer scientist to write code. Now you don't do that anymore. And I mean, that's good, but the downside is people now do statistical things that are so sophisticated that they can't actually understand. That's a whole different issue, but it really drives me a little bit nuts. It's a good question, though. It goes to the results. And then you interpret it in the discussion. Other questions? I mean, this is really important, and I know it's a lot to digest, so you might not have a lot of questions now. I don't want to do anything else today, because this is a lot, I know this is a lot to digest. There's a reason, literally, that this has all this time left over. There's 2 reasons. The first one is so you can ask questions, which you're about to do.
Can we just go through like a
Numerical example? Yes, we can. That's usually what somebody eventually asks for. What I am going to do, though, is I'm going to stop this recording.